Welcome to The Explainer. Today, we're going to talk about something that's literally all around us, but completely invisible. It's one of the most fundamental forces in the entire universe, and it powers, well, pretty much our whole modern world.
I mean, think about it. On the surface, what could sunlight, your Wi-Fi signal, and an X-ray possibly have in common? They seem like totally different things. One heats you up, another brings you the internet, and the third can see your bones. But here's the crazy part. They're all just different flavors of the exact same phenomenon. So how in the world did we figure that out?
All right, so here's the plan. We're going to look at this weird invisible dance, see how it got cracked by some master code, figure out what it means to ride a light wave, and then see how we've harnessed this whole invisible spectrum.
Okay, so let's jump back in time. It's the 19th century, and physicists are messing around with two forces that feel kind of similar but separate. You've got electricity, and you've got magnetism. Everyone had a hunch they were connected, but nobody could quite nail down how.
So it all kicked off with this discovery that must have seemed like straight-up magic. A scientist, Michael Faraday, figures out that if you just wave a magnet around a coil of wire, you can generate an electric current. Like out of nowhere. No battery, no nothing. And this showed that a changing magnetic field could actually create an electric field. That's a huge deal.
And guess what? It works the other way around too. Thanks to another scientist, Ampere, we learned that if you run an electric current through a wire, which is really just a bunch of moving charges, it creates its own magnetic field around it. You can literally watch a compass needle twitch if you put it nearby.
So this is where it gets really interesting. You've got these two ideas. A changing magnetic field makes an electric field, and a moving electric charge makes a magnetic field. Wait a minute. What if they could just create each other in a loop? Could one create the other, which then creates the first one back, in this kind of self-sustaining, invisible dance that just goes on forever?
Okay, so now it's time to bring in the main character of our story, a Scottish physicist named James Clerk Maxwell. He looked at this invisible dance and thought, that's not just a weird quirk. That's a fundamental clue to how the universe works. And he decided to write down the rules for it, not in English, but in math.
And here's the thing about Maxwell. His genius wasn't just in one new discovery. It was in taking all these different ideas from Gauss and Faraday and Ampere, all these scattered puzzle pieces, and seeing how they all fit together. He basically boiled down everything we knew about electricity and magnetism into just four. Four beautiful, elegant equations. Now, these four equations are like the rule book for the whole electromagnetic game. They explain why electric charges create fields, why you can't have a magnet with just a north pole, but that last one, the Ampere-Maxwell law, that's the absolute game changer. Faraday told us a changing magnetic field makes an electric field. But Maxwell's big idea, his what if, was that a changing electric field could also make a magnetic one. That right there, that was the piece that completed the puzzle.
And that was the whole key. With that one little addition, the dance didn't need a partner anymore. It could sustain itself. The electric field makes a magnetic one, which makes a new electric one, and on and on and on. It could just go. It didn't need a wire, it didn't need a magnet. It could literally leap out into empty space and just travel as a self-propagating electromagnetic wave. But hold on, it gets even better. Maxwell's equations didn't just say, hey, these waves might exist. No, they were like a complete user manual. They described exactly what these waves would be like, what their properties were. So deep inside the math, there was this incredible prediction. He realized he could take two numbers that scientists had already measured in their labs, one related to electricity, the other to magnetism, plug them into his equations, and calculate how fast this new wave should travel. And the number that popped out was, well, it was 299,792 kilometers per second.
And I just want you to imagine the look on his face, because everyone in physics knew that number. They knew it by heart. It was the speed of light. The number his equations spat out for this theoretical electromagnetic wave was the speed of light. The implication was just mind-blowing.
Maxwell himself said it best.
He wrote that we can, and I quote, scarcely avoid the conclusion that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Basically, he was saying, guys, light is an electromagnetic wave. The thing we see, the thing we've wondered about forever, it's just this little dance of electricity and magnetism.
And these waves don't just float around, they carry energy. I mean, think about the sun on your skin. That warmth is energy delivered across 150 million kilometers of pure empty space. And yep, there's even a part of the math for that, called the pointing vector, which is basically an arrow that points exactly where the energy is going and how much of it there is. So realizing that light was one of these waves, that was just the beginning. It was like we'd found one key on a giant piano. We soon figured out there wasn't just one kind of wave, but this huge invisible spectrum. And once we knew it was there, we learned how to play all the keys.
And this is it, the electromagnetic spectrum. It's all the same fundamental thing, that little dance of electric and magnetic fields. The only thing that separates a radio wave from a microwave from an X-ray is its frequency, or how fast it wiggles. A low-frequency wiggle is a radio wave. A super high-frequency wiggle is a gamma ray. Our eyes? They're just tiny little biological sensors tuned to one little sliver of this whole reality we call visible light. Then we got even cleverer. We figured out how to control the direction of the wave's vibration. So light coming from the sun is what we call unpolarized. The waves are jiggling around in every possible direction. Imagine a big, chaotic crowd of people all dancing randomly. But we found out you can put a special filter in front of it, kind of like a bouncer at a club, that only lets people moving in a single file line get through.
And you use this every day. That's exactly how polarized sunglasses work. The annoying glare that reflects off a wet road, that light is mostly vibrating horizontally. Your sunglasses have a filter with tiny vertical slots, so it physically blocks all that horizontal glare. And that exact same idea, filtering light, is what makes the screen on your phone, your TV, your computer, any LCD screen, work.
Okay, but here's maybe the most important thing to get about the spectrum, especially for our own health. We can split it into two big groups. On one side, you have non-ionizing radiation. Think radio waves, microwaves, visible light. They have enough energy to make atoms vibrate. That's how a microwave oven heats your food, but not enough energy to do any real damage. But on the other side, you get to ionizing radiation. This is stuff like ultraviolet light, X-rays, and gamma rays. These waves are so energetic, they can actually blast electrons right out of your atoms. And that's what can damage your cells, which is why we're careful with things like X-rays and too much sun.
So when you really think about it, it's incredible. We went from a simple question, hey, why does this magnet make a current, to unlocking one of the deepest secrets of reality. We learned to see a whole invisible universe, and by learning to control it, we built everything. Our phones, our Wi-Fi, our medical technology, all of it. It just makes you wonder, right? If all of this was hiding in plain sight, what else is out there, just waiting for us to figure it out?